All right, let's talk about something that I think every software engineer knows deep in their bones, the pain of a slow, bloated CI pipeline. But what if the fix wasn't just, throwing more expensive hardware at the problem? Today, we're going to break down a really smart technique called test suite reduction and how unsupervised machine learning is the key to making it all happen.
I mean, come on. Does this feel familiar? You push a change, you're in the zone, ready to grab the next ticket, but you can't. You're just stuck, waiting and waiting for that massive regression suite to finish. It's more than just a little annoying, right? It's a direct hit to your team's velocity and it completely breaks your flow.
Yep, we have all been there, staring at that slow-moving progress bar. That thing that's supposed to be a quick sanity check somehow balloons into this multi-hour monster that holds up an entire release. It costs time, it costs money, and it just absolutely kills momentum. But what if we could be smarter about this? And that brings us to the fix. Now, we're not talking about just going in and randomly deleting tests. We all know that's a recipe for disaster. No, this is a much more strategic approach, test suite reduction, or TSR for short. So, what is TSR, really? Well, at its core, it's all about intelligently creating a smaller, representative sample from your giant test suite. And that word representative is key. We want to do this without, and this is crucial, significantly losing our ability to actually find bugs. It's about being both lean and effective. The goal is so simple, but so powerful. Find and get rid of the redundant tests. Think about it. If you have 10 different tests that are all basically checking the same login flow, why on earth are we running all 10 every single time? TSR is about finding the one or two that really matter, so you get the same confidence and coverage, just way, way faster. Okay, so that sounds great, but how in the world do you find these redundant tests automatically without some poor engineer spending a month doing it by hand? Well, this is where we bring in the engine for this whole process, unsupervised machine learning. It turns out it's pretty much perfectly suited for this job. So this really comes down to a critical difference between two types of machine learning. With supervised learning, you'd have to sit down and manually label thousands of your tests. This one's important, this one's redundant, this one's kind of important. I mean, who has time for that? It's a total non-starter. But unsupervised learning, it skips that entire painful step. You just give it the raw data about your tests, and it finds the patterns all by itself. And that right there, the no manual labeling part, that is the absolute game changer. It's what makes this whole approach actually practical for a real busy engineering team. You don't have to hire a team of data labelers or spend weeks prepping some perfect data set. You just let the machine do the heavy lifting. It's automation at its best. So you might be asking, how does this unsupervised magic actually work under the hood? Well, the core technique is called clustering, and honestly, it's surprisingly intuitive once you see it. Let's take a look at the blueprint. It really just boils down to 3 simple steps. First, you have to turn each test into a set of numbers that a computer can understand. This is called feature extraction. Think about things like what code modules does it touch, which UI elements does it click on. Second, the clustering algorithm takes all those numbers and just groups the similar ones together into little buckets or clusters. And finally, step 3, you just pick one representative test from each of those buckets, and boom, that's your new lean and mean test suite. To make that a little more concrete, imagine you have a dozen tests for your checkout process. You've got one for Visa, one for MasterCard, one for an expired card, one for an invalid security code. You get the idea. The clustering algorithm is smart enough to see that all of these tests are really hammering the same payment processing part of your code base, so it groups them all together. Now, you can just pick one representative to make sure the core feature is still working. Okay, so this all sounds great in theory, but as engineers, we always have to ask, does it actually work in the real world? Well, let's look at the proof. There are some really compelling examples out there that show just how powerful this can be. Yeah, so the academic research on this highlights some fascinating cases. There was an e-commerce site that used a popular algorithm called k-means clustering and saw a mind-blowing 90% reduction in their test time. Then you have a totally different field, a safety-critical automotive system that used another method to maintain 100% coverage on its most critical code. And a social media app used a third type of clustering to focus on the most common user journeys while also making sure it caught weird edge cases. It really shows how flexible this approach is. Let's just go back to that e-commerce example for a second, because this quote really says it all. A 10-hour test run became a 1-hour run, and it still caught 98% of the bugs. Just think about that ROI for a minute. For any engineering team, that is absolutely incredible. It's the difference between getting feedback tomorrow and getting it before your next coffee break.
So, after digging through all this research, what are the big takeaways? Let's summarize the key findings, but let's also be honest and talk about what we still don't know, the gaps in the research.
First things first, when it comes to which algorithm to use, the research points to a very clear winner. K-means was used in 12 of the main studies they looked at. So if you're thinking about trying this yourself, K-means is a proven, reliable, and really solid place to start. And how do you measure success? Well, the top two metrics are exactly what you'd hope for as an engineer: code coverage and test suite size reduction. It tells you exactly what the goal is here, and it lines up perfectly with what we want. Shrink the suite, but don't lose that critical safety net of coverage. So to wrap it all up, the takeaways are clear. K-means is the go-to algorithm to start with, and the main goal is always to shrink that suite while keeping your coverage high. But it's also important to know the limits here. The research doesn't really talk much about scalability for truly massive systems, and a lot of these studies don't share their code, which makes it really hard to reproduce the results. That's just something we need to be aware of as practitioners. And that leaves us with one final question to take back to your team. We've seen the theory, we've seen the blueprint, and we have seen the proof. We know a 90% reduction is possible. So could K-means clustering be the thing that finally turns your 10-hour CI bottleneck into a 1-hour check? The evidence says it is absolutely worth finding out.